Today we're going to get introduced to one-sided limits and piecewise functions. I don't know if you've ever seen a piecewise function. Well, I know you've seen piecewise functions before, but I don't know if you've seen them in this form. Because the reason I know that you've seen piecewise functions is because you've seen the graph of an absolute value of x, sort of that V-shaped one. It really is two lines put together. One line with the positive slope and one line with a negative slope. And that's all a piecewise function is taking two different graphs and taking a piece from each of them, or maybe three, it can be more than one, taking a piece from each of them and then graphing it. So here we've got a function f of x. It has a piece from a line, 2x plus 1, and another piece from a parabola, x squared. Now, if I drew both of those separately, so here's my grid, and I graph 2x plus 1 in blue, so that would have a y-intercept of 1 up to over 1. There's our graph of y equals 2x plus 1. And in green, if I graph a parabola, there's my parabola. So I have both of those graphs in their entirety. What a piecewise graph says is we're going to graph 2x plus 1, but we're only going to use part of its domain. So we're only going to graph 2x plus 1 if x is bigger than or equal to 1. So I'm going to take out my eraser now, and I'm going to take away all of the graph except for where x is bigger than or equal to 1. So I'm going to erase the blue graph from here all the way to there. And my starting point on my blue graph is when I plug in 1, I got 1, 3. So that's a starting point for my blue graph. And I'm going to use my parabola only when x is less than 1. So I'm going to take my eraser out again. I'm going to erase part of the parabola until I get to x equals 1. And at x equals 1, on this graph, I'm going to have an open circle because it doesn't equal 1. So I have the point 1, 1 on the green graph. And both of those combined make the graph of f of x. F of x has two pieces. It has part of a parabola and part of a line. In this case, this function is not continuous, right? If we used our not really math definition of can't draw it without lifting your pencil, to go from the green graph to the blue graph, I would have to lift my pencil when drawing it. But this function, this is a function. Remember, how do we tell if something is a function or not? We got a vertical line test. So I can draw any vertical line, and as I move across from left to right, as long as this vertical line doesn't ever touch more than one point, it's a function. If that vertical line ever touches 2 points, it would not be a function. Now, at the point where I left it right there, it's going through the hole and through that point. So that hole doesn't actually exist. It's not part of the graph. So it still is a function based on that. So what are one-sided limits? Well, sometimes a limit doesn't exist because it only exists. In order for a limit to exist, it has to approach the same number as you get close to that value, whether you get close from the left side or from the right side. So when we have a left-handed limit, that means that we are getting close to a value from one side or from another side. So this one here, we're trying to find the limit as x gets close to 1, and the little negative up there means that we're coming from the left side. So if we go to our graph and we imagine, let's imagine, there. This is us. We're on the graph to the left of 1. and we're moving towards it. So we watch this happy face go. As we get closer and closer and closer to 1, what is our y value getting closer to? It's getting closer to 1 on the y values too. So we would say, in this case, the limit as x approaches 1 from the left-hand side of this function is equal to 1. If we wanted to find the right-hand limit of this same function, now we put a plus sign here to say we're coming from the right-hand side. Go back. Now I'm going to start on the right-hand side. I'm on the blue function. And I'm getting closer and closer to x equaling 1. As I get closer and closer to the value, I'm getting closer and closer to 3. So my limit as x approaches 1 from the right-hand side of this function is equal to 3. In this case, we would say that the limit as x approaches 1 does not exist because the left side and the right side are different. So we have a left-sided limit, we have a right-sided limit, but we don't have an actual limit. And that's what is here in this note. The right-hand limit and the left-hand limits, they have to be the same in order for the actual limit to exist. So here's just a bunch of notation. If the left-hand limit does not equal to the right-hand limit, then the actual limit as you go to that value doesn't exist. But if the left-hand limit and the right-hand limit both are equal, then they do exist. So you can make all sorts of interesting graphs that are still functions. Okay? Do you want to test your creativity? Should I give you a situation and you see if you could draw a graph that makes that work?
Yes.
Okay. So, the limit as x gets close to 2 of f of x. Let's see if we can do this without a graph. And then we'll add the graphs. I mean, the graphs are wonderful because they really help us see what's going on. But you're trying to do this mental math. If I want to find out if the limit exists, I'm going to want to check what's the limit as it comes from the left side. And if I came from the left side, which equation would I use? The top one or the bottom one? The blue one or the green one? So I'll write my answer in green. I would plug in 2 into x squared. It would equal 4. And if I was finding the limit as x comes to 2 from the right side, and you see that you would come from the blue equation, and it would equal 4 as well. So does the limit exist? Yes. And we can say the limit as x goes to 2 of f of x is equal to 4. The limit exists, and it's equal to 4, because the left-hand limit and the right-hand limit were the same. So what does this look as a graph to see that this is true? Here, I'll use. In 3x minus 2, that has a y-intercept of 2. And sometimes what I do when I'm graphing a piecewise function is, because you have techniques for graphing, right? You'd start with your y-intercept. That would be the first point that you draw. And then you have a slope of 3. You might go 1, 2, 3 over 1. That would be the next point that you draw. But those points aren't even on my graph. What I like to do is just temporarily draw the whole thing, then label the point where the value changes. So when x is 2, I have the point 2 comma 4. Notice I filled that point in. And then which piece of the graph do I want of this blue one? Just when the x values are greater. So now I'm going to fill this part in. That's the part that's actually part of my line. for my parabola, there's my parabola. Again, I'm going to label the point where it changes at 2. In this case, it's going to be an open circle at 2, 4. And the part that I'm going to include is everywhere where x is less than 2. So I'm going to fill in this section and not that part. The two graphs click together perfectly. The solid point from the blue graph fills in the open point from the green graph, and it makes it one continuous graph all the way through. And we have that the limit would exist as x approaches 2. Well, if you graphed it, do you need to show an open circle here in the end? No, because it's all included. That point gets included anyways. Okay? It gets included by this. If you drew the first equation first and made the open circle, and then you did the second equation next and filled it in, it would all be the same anyways. Try this one. And check how you did. The one limit from the left is equal to 7. The other limit from the right is equal to 15. They're not the same, so the limit does not exist. We can see that graphically. You have the parabola coming from the left-hand side, you get close to 7. You have the line when you come from the right-hand side, it gets close to 15. Here we have a pattern happening. What's the next number? And the next one? Yeah, and we're going to get pizza before long here. Almost, not quite. If this kept on going, does this sequence converge? And converge means, are we getting closer to a number? And what number are we getting closer and closer to? 2 9ths. Isn't that cool? So, what? Changing, this is just for fun, but one of the things that can be helpful is being able to change fractions to decimals. You probably know that a half is 0.5. You maybe know what's 1/3? 0.3. 0.3 repeated. At what point do you not know your fraction to a decimal? Do you know 1/4? Yeah. Yes. 1/5? Yeah. 1/6 go bad? Is that where the first time it goes bad? 1/6 is 0.16 repeated. 1/7. Oh, we.
14, 28, 56 repeating.
Yes.